Hello, this is Mr. Gilmore with the 3.1 Polygon Congruence lesson. Today we're going to be talking about a very important concept known as congruence. We already have one of the abstract thoughts of equality in play, but today we're going to talk about congruence. See, the thing about equality is that I am equal to myself, you are equal to you. However, if I were to say I am equal to you, that would be false. But congruence actually is a bit more than that. I may be congruent to myself, yes, but I also may be congruent to something else. There's may be a desk congruent to a desk. There may be a segment congruent to a segment. So even though the segments may not be equal to each other because there are two different segments, we may find them to be congruent. So congruence has a bit of a bigger relationship involved in our geometrical figures and also in our geometrical system. Let me introduce this concept of a list. So I'm going to ask you to imagine this now, but on the next slide I've got an example of this. Imagine that we have a polygon in front of us. So make it any size. Make it 3 sides, 4 sides, 10 sides, however big you want to make it. But imagine that we pick a starting point on the polygon. That starting point could be a vertex, or it could be the side. But what I want you to do is I want you to travel around that polygon. And each time you come to a side or to a vertex, at that vertex there's a measure of an angle, and at that side there's a measure of a side. So imagine that we have in our brains this polygon, and we're traveling around it, and every time we encounter a side or a vertex where the angle is, we know its measure. And as we do this, we're going to list out all the sides measures and all the angles measures. So let's actually then take a look at constructing a list. I've got an example here for us. So here's an illustration of our polygon ABCD. Now at each angle, I have the angle measure labeled, and at each side, I have the side measure labeled. So we start at our vertex A, where the angle measure is. Its measure is 62. We then move a direction around the polygon, and we can keep in that same direction. So let's then move from point A to point B, but as we do that, we travel along the side AB. And that side has a measure, 2.2. And then we reach vertex B, and that has a measure to the angle of 98 degrees. And we continue all the way around until we've produced a list. So now we have a list of these numbers, and you should see a pattern in these numbers. It alternates side, angle, side, angle, side, angle, right? And so we're going to see that for every polygon that we can produce, that polygon produces its own list of its angle measures and its side measures. Now, what if we were then to produce a second polygon that it also had the exact same list, the identical list? So in our second polygon, we'll call this PQRS. If we also started at point P, which has an angle measure 62 degrees, and we move in the same direction as we did in our first polygon, then we're going to produce identical lists. Each and every single one of those measures will match up with a measure from the other polygon. When this happens, when we actually have an identical list from two polygons, two or more, I should say, we may call those polygons congruent to each other. So let's give this definition a precise definition. Let's give this term a precise definition. Before we get into it, let me introduce a word called correspond or corresponding. So let's say we build two such lists. We have a list for one polygon and a list for the other. When the measures are in the same position, we say that they are corresponding. So in other words, and we'll take a look at this, in other words, in our diagram, angle A and angle P corresponded with each other because they were in the same position. So now we have this new word name, or we have a new term called correspond or corresponding, then let's use that in our definition for the word congruent. So by definition, we can claim or declare two polygons congruent if we can build lists for the two such that the angles and the sides which correspond are equal. So let me say that again. If we can build two lists such as the two for the two, such that the angles and the sides which correspond are equal. In other words, when we match up the corresponding parts and all the corresponding parts in that list match up, then we may declare those two polygons congruent. So let me ask you this question. Are these two triangles here congruent? Well, let's take a look. Are we able to match up corresponding angles and produce the exact same list if we have the corresponding angles and the corresponding sides? Let's start at point A. on the first triangle? Well, point A is marked with an angle measure of 3 hash marks. Well, if we have another angle measure in our second triangle with also 3 hash marks, it matches up with point F. And I travel from point A to point B. Well, if I travel from point F to point E, they're also marked with the same marking, which means we know they're equal. We reach point B and point E, and we realize that those angles are equal. Traveling from B to C and E to D, we have those two sides as being equal. C and D are also marked as angles being equal, and then our last segments, C to A and D to F, are also being marked as equal with triple hash marks. So do these two triangles produce the same list? They do. Now notice that we traveled in a different direction. From A, we traveled in a clockwise position. But for F, we traveled in a counterclockwise. But we were still able to produce the same lists. So here's our very first lesson with congruence. Our first lesson is if we can still build identical lists, and sometimes we have to travel in different directions around the polygons. In one, we traveled clockwise, and the other, we traveled counterclockwise. So we don't always have to start in the same place, right? A did not have to start with D. A started with F. And so in this case, it may be a left side on one triangle, but that right side on the other, which actually correspond with each other. But we can still produce the same list. So yes, those two previous triangles were congruent. They could produce the same list. Are these two congruent? Well, let's observe. As I'm taking a look, I see, let's say, angle F and angle B are the same measure. Angle A and angle H have the same measure. D and G have the same measure. C and E have the same measure. I also see that the same four side measures of the first have a corresponding equal side measures of the second. But notice there's something wrong. Okay, as I travel from A to B, in our first diagram, I travel from a right angle along the side that is 2 to another right angle. But if I try to do that in, let's say, our second diagram, if I travel from point F to G, well, I started at a right angle and traveled along the side 2, but I did not end up where the right angle was. So if we take a look, do these polygons produce the same amount of equal angles and equal sides? Yes. All sides of the first are equal to all sides of the second, and also all angles of the first are equal to all angles of the second. But the lists are not in the same order, right? If I were to produce the list of the first and produce the list of the second, yes, they would have the same numbers, but the orders would not, or the order of those numbers would not be in the same order. So here's your second lesson. Just because we have equal angles and equal sides of one and another doesn't make it enough. We have to make sure that the lists are exactly identical to each other. So when we build the list of the first, it must be able to match up and produce the second list of our second polygon. If it doesn't match up exactly, we do not have congruent polygons. We have a symbol in mathematics to represent congruence. It's related to the equal sign. As you can see, we see in the symbol of congruence, we have those two bars represent equal sign, but then there is a tilde placed over top of it. So that is what we can then use to describe polygons being congruent with each other in symbolic form. So if I were to bring two polygons together and declare them congruent, instead of actually writing it out in words, I may place this congruent symbol between them to represent the congruence between the two polygons. So when we bring our polygons together and we put this congruent symbol in between them, we simply just name the polygon on the for the first polygon on the left and give the name of the polygon of the second polygon on the right. However, when we place names of those polygons in there, we must consider the order of the names. Let's talk about that a little bit. Order matters. We're going to take a look at, in just a second, writing out a congruent statement for two polygons that are congruent. We must make sure that the letters which correspond of the first match up with the corresponding letters of the second, meaning that from the congruent statement, I may know which angles and which sides correspond already from just the name. So our naming system for our polygons and the order in which we name them in our congruent statements is extremely important. So they must be in the same position. If A were to correspond with P, then A and P must be in the exact same position in our congruent statement. Let's take a look at some examples. So we had these two polygons earlier, and we can already produce the same lists for these, which means, yes, these two polygons are congruent. Point A and point P have those angle measures of 62 degrees. Well, that means A and P inside my congruent statement must be in the same position. So A and P, wherever they're at, if they're in the first position, then A and P must be in the first position. If B is in the second position, then Q must also be in the second position because B and Q correspond. C and R correspond, and D and S correspond. Which means if I kind of have a freedom in the very first choice, I can choose the order of my first polygon. But when I've chosen that order, I must respond in the same order to my second polygon. So let's take a look. A, B, C, D, P, Q, R, S. That is a valid name of our two congruent polygons here because A and P correspond, B and Q correspond, C and R, and D and S. Let's take a look at a second version. Remember, you have different variations of naming a polygon. So let's say I went CBAD. Well, I can respond then by naming my second polygon in the same corresponding fashion, RQPS. But below, take a look. These two are invalid congruent statements. Yes, in the first example here, A and P do correspond. That does match up. But look at B and S. Those do not correspond because B and S are not in the same position. B and Q must be in the same position, which means that's not a valid name. So there are many, many ways you can write out a valid congruent statement, but there's also many, many ways that you can mess it up and write an invalid congruent statement. See, the statement itself is powerful. You can use the statement itself to actually find information about the congruent polygons. We're going to see at the very end of these slides some examples of where I'm given the congruent statement, and from the statement I can match up my corresponding parts, meaning I know which angles correspond and I know which segments correspond just from the name of the polygon. So one quick consequence of congruence is if we are given that polygons are congruent, if we're already told that two polygons are congruent, then a quick consequence of this is we already know all the corresponding parts are equal to each other. All the angles are equal, and all the corresponding sides are equal. So I can actually match up from my given congruence already which angles I know to be equal in measure and sides equal in measure. This is going to be an important concept later for us when we jump into our proofs of congruence. We'll see that if we have established congruence, then we already know that we have corresponding parts that must also be equal. We have a name for this. Some people call this CPCPE, which stands for corresponding parts of congruent polygons are equal. CPCPE. So corresponding parts of congruent polygons are equal. So if we have declared or we are given congruence between two polygons, then we can already establish that their corresponding parts have to be equal. Now, if we're specifically referencing triangles, which you'll see later on in this chapter, we will be specifically referencing triangles, we can replace the word polygons with the word triangles. So instead of CPCPE, we can say CPCTE. So I want to make sure, and we'll hit home on this later on in the chapter, but in order for us to declare that we know corresponding parts to be congruent, then we have to know the polygons are already congruent first. So from congruence, we can then produce CPCTE. Now let's do an example to finish off the lesson. So let's assume we have these pentagons that are given to us as being congruent. ABCD, the pentagon ABCD, is congruent to the pentagon ZYXWV. Now, remember, the order of our name is extremely important. It already tells us which parts correspond, and more than just which angles correspond, because I know which segments are connected, right? Adjacent segments are going to have the vertices in the name adjacent to each other. So since A and B are adjacent to each other, then I know that I have adjacent segment Z and Y. Those would be corresponding. And I know then what follows from this. From CPCTE, the corresponding parts of congruent triangles are equal. I know I can declare corresponding angles and corresponding sides as equal to each other. So if we take a look at our examples, I want to know what angle A's measure is equal to. So it has a corresponding angle of the second polygon. Well, all I have to do is follow the position of angle A. Angle A is in the first position, which means angle Z, also in the first position, are the same, which means I can fill this in as saying the measure of angle A is equal to the measure of angle Z. Why? CPCTE. The corresponding parts of congruent triangles, I really should say polygons here. Corresponding parts of congruent polygons are equal. A and Z are equal. Let's do the next one. W. Well, I consider then my second polygon. W is in the fourth position. Well, what letter of our first polygon is also in the fourth position? It's point D. That which means angle D is going to have the same measure as angle W. I get that just from the name. I don't need a diagram for these two polygons. I have enough from the name to declare equality and know which angles and segments correspond. Let's look at segments now. CD. Well, if I'm taking a look at my first polygon, C and D are in the third and fourth position, which means which letters are also in the third and fourth position of my second polygon? X and W. So I know that CD is going to be equal to XW. They're the same measure. Why? It all comes back again to CPCPE. Corresponding parts of congruent polygons are equal. Last but not least, we've got one more segment to compare. Let's look at VZ. So VZ is a part of my second polygon. V is in the fifth position, and Z is in the first position. But those are adjacent, right? Those would be adjacent. If I were to draw the diagram, Z and V would connect, which means I'm also considering in my first polygon what's in the fifth and what's in the first position. Take a look, E and A. So there we have EA. That is our segment that's also equal to our measure of VZ. And again, it all goes back to CPCTP or CPCPE because we already are told that these two polygons are congruent. This concludes the end of our 3.1 lesson. If you have any questions over this lesson, please email me. I will get back to you. With that, be good. Oh, sorry. With that, you should be working on the 3.1 worksheet and make sure, right, if you do come across any questions that you need help on, you reach out to me, right? Polygon congruence is extremely important, okay? It's extremely important because we're going to be using this polygon congruence the rest of the year. We're going to be using it to prove congruence between triangles, and the proving of those congruence between triangles is going to be a huge part of our discovery in the system of our geometry, in the discovery of our geometry system. So yes, please be working on the 3.1. Ask questions if you need any. Now with that, be good and do good.